In this problem, we're going to be determining the Kb of a solution given the concentration of your base and the pH. One thing that is great about this problem compared to the other ones is using the pH, we can solve for the concentration of our hydronium ions. And using a balanced chemical equation, we actually don't have to solve for or use a Rice table in order to solve for any of these. And so starting off with the information that we're given and what we know about bases, we can, again, write the general equation or reaction equation for the base, and we can also write our Kb equations because, again, those are very general. They're not going to change when we start talking about these weak bases. And so the general equation for the base still includes adding the base to water and it becoming an equilibrium reversible reaction with your Hb plus and your OH minus. The Hb plus is just the conjugate acid of your base. OH minus is the same thing it's always been. It's your hydroxide ions that are formed when you dissolve a base into water. The Kb is still just going to be the multiple of your Hb plus and your OH minus over the B. In this case, as before, your H2O is left out of the equation because we're considering a pure substance that will not change its concentration. And so as I mentioned in the beginning, your pH, it tells you something about your hydronium concentration. And so using the equation of pH in order to solve for your hydronium ions, we can say that our H3O plus is equal to our negative pH, 10 raised to the negative pH, or 10 to the negative 8.5 will give us a concentration of our hydronium ions as 3.2 times 10 to the negative 9. And so once we know our hydronium ions, using an equation involving Kw, we know the fact that our hydroxide concentration times our hydronium concentration is going to be equal to Kw, our Kw being 10 times 10 to the negative 14. And so plugging all these into what we know here, our hydroxide ions are going to be equal to the 10 to the negative 14, or Kw, divided by the concentration of our hydronium ions. And so the hydroxide equals 10 to the negative 14 over 3.2 times 10 to the negative 9. In this case, we end up with our hydroxide concentration as 3.2 times 10 to the negative 6. So now we know our hydroxide concentration. Given a balanced chemical equation up at the top, I tell you that for every 1 mole of base that decomposes, you're going to produce 1 mole of Hb plus and 1 mole of hydroxide ions. So at equilibrium, that Hb plus and that OH minus are going to be the same exact concentration because that's just how it works out. And so here, if we know the concentration of our Hb plus, of our OH minus, we also know the concentration of our Hb plus. And again, this concept can be reviewed in the previous practice problems that I've kind of already recorded. So we kind of go through and just plug these values into our Kb. We know our Hb plus is going to be 3.2 times 10 to the negative 6. We know our OH minus is going to be 3.2 times 10 to the negative 6. And so on the numerator, you have 3.2 times 10 to the negative 6 squared. We know our B, or concentration of B, because it's given to you in the problem. And so from there, again, you can solve for the Kb of 3.2 times 10 to the negative 6 squared divided by 6.0 times 10 to the negative 3, or Kb is equal to 1.7 times 10 to the negative 9. And so as I stated before, that very small value for Kb means the fact that this reaction is going to prefer your reactants over your products. So very, 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 very little amount of that base is going to decompose into your Hb plus and our OH minus. And so I've stated this in the past, but I kind of going to show you an example here. This whole problem could have been worked out a completely different route. And so the pH, that's going to be solved for the same way. You can't really kind of change that. But once you know your concentration of the hydronium ions, you could have gone through and just used this equation of pH equals your POH. And so pH plus or POH has to equal, again, the pKw. pKw is always going to be 14. And since we're given your pH, then you can solve for the POH of 5.5. If we want to know the concentration of our hydroxide ions, do the same thing that we've done with like the the hydronium ions earlier, but from the pH, we can say that POH is going to be, the concentration of our hydroxide ions is going to be equal to 10 raised to the negative POH, or 3.2 times 10 to the negative 6. And if you compare that concentration of hydroxide ions to the concentration of the hydroxide ions we solve for using the completely different route, you still end up with the same number because they're all still going to be interrelated to each other.